Okay, today we're going to do another related rates problem. At noon, ship A is 100 kilometers west of ship B. Ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. So, how fast is the distance between the ships changing at 4 p.m.? So, let's write down what we know and do a little diagram because that's always going to be step one. So, we have a point here. We have a point here where we have ship B and we have ship A over here. And we know that we're looking at the time frame we're looking at is noon to 4, which means that we're saying whatever we're looking for it after 4 hours, right? At 4 hours. Well, what exactly do we want to find at 4 hours? We need the diagram to find out what exactly that is. So we've got ship A here, okay? We've got ship A. And we've got ship B. Now, what do we know? At this point in time, at noon, they're 100 kilometers away from each other, right? A is 100 kilometers west, so this is west of ship B. So we know that this right here is 100 kilometers. 100 kilometers. Okay, so far so good. Now, what else do we know? We know that at noon, this is how they stand, and then from noon until 4 o'clock, they're moving in different directions. Ship A is sailing south at 35 kilometers per hour. So we're having ship A, let me actually not do that way. We're having ship A move south. We're having ship A move south like this. Well, that's the opposite direction of where B is moving because B is moving up. B is moving up north at 25 miles per hour like this. So, well, what are we supposed to find? Like, it gets a little confusing. I was a little confused at first when I first did this problem, but basically, you're going to have to visualize the triangle, right? Because there's usually a triangle. What we're going to look for is this length here. So let me explain. We know that we're looking for how fast the distance between the ships A, which is at 4 p.m., it's here, and B, which at 4 p.m. is here, is changing, right? After 4 hours. This distance right here, let's call this distance, let's call it Z. Okay? Well, we can set up an equation next. That's our next step. But how do we do that when we don't really have a triangle? We have two triangles. Well, that's a little confusing, but not really, because we also know that where this length ends, this length starts. Let me label them. Let's call this y, and let's call this x, right? Well, we know that this is y plus x, and we know that this is 100 kilometers. So we actually have two lengths. Sorry, we have two rates even for the lengths. 100 kilometers, and this right here is x. So let me just also write down that we know that this entire thing, well, I don't know what happened there. Oh, I see. I think because this is like that this entire thing is x plus y. Okay, well, that means that we're going to be able to use the Pythagorean theorem, doesn't it? But before we do that, before we actually set up our equation, let's write down our rates as well. We know we have two rates given, don't we? We know that A is moving 35 kilometers per hour, and B is moving at a speed of 25 kilometers per hour, which means that the change in the distance of B, so the change in y over the change in time, is 25 miles per hour, is 25 kilometers per hour. Great. So we've got the rate of change of y. Do we have the rate of change of x? We do have the rate of change of x. We know that the change in x over the change in time, which is the rate of change of x, is 35 kilometers per hour. I keep wanting to say miles, but if you hear me say miles, just think, no, she means kilometers. Okay, So what does that mean? It's not going to be hard for us to find out what the length itself is here for z, because we have the length of y and x and so on and so forth. Because we have these rates, we're just going to have to plug it into our equation, right? So that means that what we're actually looking for, and that's why I'm not just explaining it slowly, because we want to run through it to find out what we're looking for real quick first, and then do it step by step. What are we looking for after 4 hours? The change in the distance between these ships after 4 hours, which means we're looking for the change in z over the change in time. We're looking for the change in z over the change in time, so the rate of change of z. That is what we're looking for. Okay, so with that in mind, let's set up our equation. Now we see that there's a triangle here, and it's perfectly reasonable to assume that this is a right triangle because of the way that we've set it up. And therefore we know that z squared is going to be 100 kilometers squared plus y plus x squared. So that makes sense so far, right? Well, what do we want to do before we start to differentiate this and try to figure out what the rate is? We want to figure out what x, y, and z are after 4 hours. But that's pretty easy because we can find out what x is after 4 hours, because we know that the change of rate of x over time is 35 miles per hour. 4 hours, 4 times 35, and therefore x, which is 4 times 35 at 4 hours, at 4 hours is going to be 140. So with what we're working, we know x is 140, and y is going to be 4 times 25 at 4 hours, which means it's going to be 100. So that means that y and x, we're going to have them. Well, we're going to use these lengths. We're going to use them to find z. What is z going to be, given that we know that the Pythagorean theorem applies? We know z is going to be the square root of 100, which is this length down here, of 100 squared, plus x plus y squared. But x plus y are 140 and 100. So that's 100 plus 140 squared. And you can put this in your calculator if you want to make sure it's true, but what it actually comes out to is 260. 260. So now we have our 3 lengths. This is a little messy. Let me write it all down in the corner here, because now we know it. We know x is 140. We know y is 100, and we know z is 260. Okay, so now I'm gonna get rid of this side work because we need the space. So let me just do this. Okay, so now let's go back to another color. Let's get to the actual work of the actual equation. So like I said, we know that z squared is 100 squared plus x plus y squared. So what do we do with this? Well, we use implicit differentiation. Implicit differentiation, so that we can find the rate of change of z and isolate it and solve for it, right? Differentiation. And that is why we're taking the derivative of both sides. We can't just do one side. We have to figure out how to isolate the rate of change of z. We're going to have other rates of change in here. So what we're going to do, we're going to start to simplify this a little bit. And we're going to take the derivative of z squared, which is going to have a chain rule because z and t have a variable mismatch, but I will write that down the long way. Z squared over dt, and there's going to be a chain rule here. So the outer function is going to be t squared, and the inner function is going to be z. So we're going to take the derivative of z squared with respect to z, and then multiply it by the derivative of the inner function, which is going to be dz by dt, which is what we're solving for, right? But I'm not going to do that quite yet. I'm going to end up with the derivative of 100 squared is 0 because the derivative of any constant is 0. And then the derivative of x plus y squared, also going to require a chain rule. So the outer function here is also t squared. So we're going to take down that 2, right? 2 times the inner function to the power of 1. I'm not going to write that, although actually I could, why not? So we've taken the derivative of the outer function, we've put the inner function in it, multiply that by the derivative of the inner function, which is going to be the change in x over the change in time plus the change in y over the change in time. But no worries, because we know what that is. Okay, so now on this side, because there's a chain rule here, we're actually going to end up with 2z times the rate of change of z. Now that's what we're trying to isolate that. So, and on this side, we're going to end up with, see, that looks like I'm taking the derivative. Actually looks like I want to take the derivative of x plus y. It's supposed to be a 1. I'm just trying to visualize here. So I'm going to take that away. Okay, so now what we have is 2z times the rate of change of z. And on the right side, we have 2x plus y times, now this is together, just so that's clear, times the rate of change of x plus the rate of change of y. We're going to start plugging things in there pretty quickly. But what I want to kind of make a point of is that we're trying to get this alone, aren't we? So we're going to divide by 2z. So we're going to divide by 2z, and we're going to divide both sides by 2z, obviously. And we're going to therefore end up with the change in z over the change in time. So on this side, now we're going to start putting our values in. Well, first thing that we're going to realize, because this is together, is that we can get rid of these 2's, can't we? We can get rid of these because you're multiplying 2 by all of this. So you can just get rid of these 2's, and we're going to end up with x plus y times 35 plus 25, because we know that those are the rates. We were given those rates in the beginning. And all of that over z. And we know that z is 260. And now we're going to plug in 140 and 100 for x and y. So we're going to end up with 140 plus 100 times 35 plus 25 all over 260. And the solution to this is going to be 720 over 13. And now don't forget your units, that's kilometers per hour. So that is the change in z over the change in time. And what that means is that the distance between these ships after 4 hours is changing with a rate of 720 over 13 kilometers per hour. And that's our solution. I hope that this was helpful.